Hello. Thanks to the organizers for the opportunity to speak here. This talk is about the algorithmic phase transition of random KSAT for low-degree polynomials. This is joint work with my advisor, Guy Bresler. In random KSAT, we generate a KCNF formula with m clauses by sampling all the literals IID and uniformly from n propositional variables and their negations. This problem is parameterized by a clause density, the ratio of clauses to variables. There's two natural questions one can ask about this problem. First, at what clause densities does a satisfying assignment exist? Second, at what clause densities can a satisfying assignment be found by an efficient algorithm? Call these limits opt and alg. It turns out opt is larger than alg, so a third natural question is, what prevents efficient algorithms from succeeding beyond alg? We work in the following double limit. Let k be a large constant, and let the clause density alpha be a function of k. Having fixed these values, we send n to infinity. In this limit, opt is the value shown here, about 2 to the k log 2. Its exact value was confirmed in the landmark paper of Ding, Sly, and Sun. We focus our attention on alg, for which much less is known. The current best algorithm is FOCS by Kojo Oglon, which finds a satisfying assignment at clause density about 2 to the k log k over k. This is nearly a factor of k smaller than opt, so there's a big information computation gap. Moreover, there's heuristic structural evidence that this gap is inherent, and no efficient algorithm can do better. This is because around clause density 2 to the k log k over k, the solution space exhibits a dramatic shattering phase transition, changing from one big cluster to exponentially many small clusters. In the clustered regime, local search heuristics become powerless, and this is some evidence that algorithms should fail. We confirm this heuristic picture to a large extent. We show that due to shattering, the class of low-degree polynomial algorithms can't solve random KSAT at a constant factor, about 4.9, above 2 to the k log k over k. Low-degree polynomials are a computation class where each output is a degree d polynomial in the inputs. We think of d as about log n, hence low degree. We can allow the polynomial to be random, but it turns out randomness doesn't buy us more power. Roughly, this is because we can always run a random polynomial deterministically on its best random seed. So for the rest of this talk, we focus on deterministic polynomials. Low-degree polynomials simulate state-of-the-art algorithms for random KSAT and other average case problems. Notably, this includes FOCS and the famous message-passing algorithms, belief and survey propagation guided decimation. So the failure of low-degree polynomials is strong evidence of computational hardness. We show hardness for the following notion of solve. We can encode a KSAT formula as a vector of indicators. We use a one-hot encoding with 2n indicators for the possible values of each literal. This vector will be the input to our polynomial. We say a low-degree polynomial solves a KSAT formula phi if, when we run the polynomial on this encoding, the sign of its output is almost a satisfying assignment. Here, almost means that we can be wrong in a small fraction of bits, and when we correct those bits, the resulting assignment can fail to satisfy a small fraction of clauses. This is a relaxed notion of solve. Note that relaxing the notion of solve makes any hardness result against it only stronger. We also require a normalization condition on the polynomial. We won't worry about this. All the above algorithms can be implemented in a way that respects this condition. We can now state our main result. Let kappa star be the constant shown here, about 4.9. Our result is that at clause density kappa times 2 to the k log k over k, for any kappa larger than kappa star, no low-degree polynomial solves random KSAT with the success probability shown here. This probability scales with the polynomial's degree d. Note that this probability is quite large, and the limitation of our methods is that for low-degree polynomials, we only rule out a large success probability. But we can show that the more restricted class of local algorithms, which can nonetheless simulate FIX and message passing algorithms, can't solve random k-sat with even very small probability. Moreover, at clause densities where algorithms succeed, they can be implemented by both computation classes and succeed with probability larger than even that ruled out by the first theorem. This result is part of a long line of algorithmic lower bounds on random k-sat. I want to highlight two of these results. Gamarnik and Sudan showed balanced sequential local algorithms fail to solve random not all equal k-sat at clause density 2 to the k minus 1 log squared k over k. This gets within a log k factor of the truth. Our proof takes inspiration from this paper, which uses similar overlap gap techniques as our methods. Also, Hederick showed that survey propagation guided decimation fails anywhere above the believed value of alg. Our contribution is the first hardness result against any class of algorithms that gets within an absolute constant factor of the truth. This is also the first class that includes FIX, which gives us matching upper and lower bounds a constant factor apart. The proof is based on the overlap gap property, an idea introduced by Gamarnik and Sudan that connects clustering and the failure of stable algorithms. There's a rapidly growing body of hardness results from OGP. Here's a partial list. Let's first introduce the classic OGP. Say we want to prove that low-degree polynomials fail at some clause density in the hard regime. First, we show that at this clause density, with high probability, a constellation consisting of two satisfying assignments, a medium distance apart, doesn't occur. The absence of this constellation is a formalization of clustering. Second, we show that if a low-degree polynomial finds a satisfying assignment, it can be used to construct this constellation. By contradiction, this means that low-degree polynomials can't find a satisfying assignment. It turns out the classic OGP proves low-degree polynomials fail above some intermediate clause density, below oct but still well above alg. This settles part of the hard regime. I'll first show the classic OGP argument, which amounts to a simplified version of our proof. And then I'll explain how to improve this argument to show hardness within a constant factor of alg. Suppose for now that we're above the intermediate clause density. We construct the following path of correlated k-sat instances. The first k-sat instance, phi0, is drawn from the k-sat distribution, and each subsequent one is generated by resampling the tth literal of its predecessor. In other words, we resample the literals one by one until we've resampled them all once. This means the first and last phis are independent, and the middle ones have some mixture of the literals of these two. We consider the following forbidden structure. Two assignments, each satisfying some phi in the interpolation, not necessarily the same one, a medium Hamming distance apart. Medium will mean some critical value that we'll determine. We can prove this structure doesn't exist by a first moment argument. We can plot the log expected number of pairs of satisfying assignments at each overlap value, and we find that it looks like this. There's a dip in the middle where the plot is negative. At these overlap values, the expectation is exponentially small, so with high probability, these overlaps don't occur. Now we leverage this structural property to show that low-degree polynomials fail. Suppose for contradiction that a low-degree polynomial solves random k-sat with sufficiently high probability. This is the large probability ruled out in the theorem. We run the algorithm on all the k-sat formulas in our interpolation to get a sequence of assignments x. By a union bound with high probability, all of the x's satisfy their corresponding phis. In this cartoon, I've drawn x0, and the red moat is the assignments at medium distance from it. I've also drawn the last x. This will be far from x0 because the corresponding phis are independent, and with high probability, independent k-set instances don't have satisfying assignments that are too close. If we follow the x's, by the stability of low-degree polynomials, we only ever move by small jumps. So we can't jump over the moat. We eventually get to the other side, though, so at some point we land in the moat. But now, x0 and whichever x landed in the moat are a pair of assignments, each satisfying some phi, a medium distance apart. This is a contradiction, so the algorithm A can't exist. As we just saw, the classic OGP proves hardness above the intermediate clause density. In the remaining hard regime, the argument breaks down because the two-solution constellation isn't forbidden anymore. To handle this regime, the key idea is to use a bigger constellation, consisting of several satisfying assignments. This idea is called the Multi-OGP, and it will let us show hardness a constant factor above alg. This idea was introduced in the study of maximum independent set, where it tightly characterized the asymptotic algorithmic threshold. Our work will generalize these techniques. Here's some intuition for why the multi-OGP should help. We can plot the same log first moment as before at the clause densities we're interested in. This plot doesn't go negative anymore, and in fact, the structure is not forbidden. But the plot still has a dip. This means that even though medium overlaps aren't forbidden, they're still rare. In fact, since we're plotting a log, these medium overlaps are exponentially rare. So, if we design a forbidden structure with a lot of these overlaps, we can hope to boost the unlikeliness until the log first moment goes negative. The overall shape of the argument is the same as before, but with a more complex constellation. Of course, this change causes both parts of the argument to become more involved. Let's now see the enhanced argument. Suppose we're above the clause density in our theorem. We construct a similar interpolation as before, where we start with a random k-set instance v0 and resample the literals one by one. This time, after we've resampled all the literals, we loop around to the first literal and do it again, a total of k times. So now any two phis at least km time steps apart are independent. The forbidden structure consists of k assignments, each satisfying some phi, such that each assignment after the first is a medium multi-distance from its predecessors. We'll define the meaning of multi-distance later. The notion of multi-distance is carefully chosen so that by a first moment argument, this forbidden structure does not occur with high probability. Taking for granted that this structure is forbidden, let's first see why low-degree polynomials fail. As before, we argue by contradiction. Suppose the algorithm succeeds with the large probability ruled out by our theorem, then by a union bound, with high probability it succeeds on all the phis in the interpolation. Let's look at the sequence of outputted assignments, x. I've drawn x0, and the red moat is the assignments at medium multi-distance from the singleton set x0. By independence, the x that's km time steps in the future is outside of this moat. We construct the forbidden structure one assignment at a time, starting with y1 equals x0. Like before, we follow the sequence of x's, and we only move by small jumps. We eventually get to the other side of the moat, but we can't jump across it. So we eventually land in the moat. And whenever we do, we let y2 be that x. Let's say x4. Now we consider the new moat of assignments at medium multi-distance from this pair. By independence, the x that's km time steps in the future is outside of this moat. And we eventually land in this moat too. So let's call that assignment y3. And so on. Since we add an assignment to our structure every km steps, and the interpolation goes on for k squared m steps, we complete the structure before we run out of assignments. So this constructs the forbidden structure. And by contradiction, that means the algorithm can't exist. The main challenge of this proof is showing the forbidden structure does not occur with high probability. There's two parts to this difficulty. First, we have to pick the right notion of multi-distance, or equivalently the right modes on the previous slide. If we don't, the structure will not be forbidden at the clause density that we want. Second, we have to show that the expected number of copies of the forbidden structure, defined with the correct multi-distance, is o1. Achieving this for random case set requires new ideas. In maximum independent set, where the multi-OGP originated, the forbidden structure consists of large independent sets, where each independent set has a medium non-intersection with the union of its predecessors. The multi-distance in this setting is non-intersection with union. This elegant construction works because in maximum independent set, the first moment of the forbidden structure is controlled by the number of edges in the union of the independent sets, and these edges are independent random variables. This allows very accurate estimates on the first moment. Unfortunately, the corresponding first moment in random case set has complex dependencies, which makes the construction and analysis of the corresponding forbidden structure significantly more difficult. Solving these challenges for random case set is the main technical content of our work. We design the multi-distance for random case set and conduct an involved first moment analysis to show that this structure doesn't occur. I'll end by showing how to define the multi-distance and forbidden structure. We'll need a notion of overlap profile. Informally, this summarizes all the ways that L assignments, y1 through yl, can agree or disagree. The overlap profile is a length 2 to the l-1 vector. Formally, it's indexed by unordered partitions of 1 through L into two sets. The entry indexed by the partition st is the fraction of coordinates where all the y's indexed by s agree and all the y's indexed by t agree. The overlap profile can be thought of as a probability distribution. The entry pi_st is the probability that at a uniformly random coordinate, all the y's indexed by s agree and all the y's indexed by t agree. We can define the overlap entropy as the entropy of this distribution. This measures, in some sense, the diversity of the set y1 through yl. The reinterpretation of the overlap profile as a probabilistic object is an important step of our analysis because it allows us to use information theoretic tools to study this combinatorial problem. We can now define the forbidden structure. We define the multi-distance from yi to its predecessors as the overlap entropy of y1 through yi minus the overlap entropy of y1 through yi minus 1. This is the additional diversity that yi adds to the collection. It can also be thought of as a conditional entropy. We also define beta star to be the constant shown here, about 3.5. The forbidden structure is defined by plugging this multi-distance into the earlier definition. So the medium multi-distance condition requires the multi-distance from each assignment to its predecessors to be about beta star log k over k. The main argument of our paper shows by a first moment analysis that this structure doesn't occur. In summary, low-degree polynomials don't solve random k-sat at a constant factor clause density above alg. More broadly, I believe the multi-OGP methodology generalizes and can show algorithmic hardness in a variety of average case problems. An important open problem is to close the remaining constant factor gap, and another open problem is to generalize OGP hardness results to other random optimization problems, such as random CSPs and perceptron models. That's all I have. Thanks for your attention.